as I mentioned, these algorithms work on processing elements in collections, but they are not defined for specific collections. They are defined via iterators. And on Monday I showed you how the algorithm work in a general way. They are not member function of the containers with this global algorithm we are talking about. And the linking tool between algorithm and containers are this notion. As you can guess, separating behavior from data is not quite an object-oriented approach, but this was chosen for performance issues and for speeding up the learning. If you have one sort algorithm, you can apply to various data types. You don't have to learn about 5 different sort algorithms, one working on vectors, one on lists, and one on double-ended queue, one on C arrays somehow. Each algorithm is very general, does not have to be rewritten for each container. And we will look, the benefit is this, the downside is they come with conditions. You have to know about those conditions in order to use them properly. So it's a learning curve. When you need to use something, you have to go to the reference page and read about that tool before using, because you can go into trouble quite easily. So as you can see, we have min algorithm and min element, and the minimum algorithm, which is provided in 98, came in 2 forms, and you can see it's a templated function, right? Minimum return a constant reference, the smallest value, and takes 2 constant reference types values. Notice, reference constant, it's the way to pass arguments to functions, which I try to specify. Now, as you can see, there is a version where you can pass the 3rd argument, the comparison. By default, the comparison, it's written there somewhere, is the smallest, A less than B. But this comparison can be changed. If you design your types, you can provide your own comparison method. So the 3rd argument is a function. Now, as you can see, this is an overloading of templates. 2 arguments or 3 arguments. It's possible to have overloading. And now, look at how this is implemented. And this is a good place to see how you would approach your assignment 2 part 2, because you have to write functions like these, templated functions, which are method of a class. But as you can see here, you can look at how comparing is performed. These are very good places to find out how to write a good function. So it's interesting that they use the ternary operator, and they say not B less than A. If this evaluates to true, it means that A is less or equal to B, right? If A is less or equal to B, A is returned, otherwise B is returned. There are efficiency reasons why they use not and less as compared to A less or equal to B. Apparently this combination of not and less is more efficient than calling less or equal to B, because that has two functions behind. Anyway, so this is a good place to look at how algorithms are implemented. And here you have some explanations. Where C11 initializer lists were introduced, and C11 here, you can see now we have more functions for minimum because of this third case, which we will not cover as we haven't talked about initializer lists. And after you have the function equivalent to, so an example of how the code is written, you have here some example how to use it and what is the output, of course. Now, linear in one less than the number of elements compared. So it's constant for one argument for this thing, because for two arguments here, for version 1 and version 2, is constant time, so it's very efficient. And it's clear from here you don't have to perform a lot of going through elements in your container. But this is how minimum works. And then we have minimum element, which works with ranges. And here you see implementation of the algorithm using iterators. Right? Minimum element takes a range, first and last, given by they have to provide operators for what we have seen for forward iterators. And this means read-write access to elements in the container plus comparison between iterators. This is the main thing here. And you can see first part, it's comparing if we have an empty range, last is returned. Remember, if you have a vector, last means the element which is after the last significant element. So if you apply this to a vector begin, vector end, last means something which is not dereferenceable. So this is important. For many algorithms, you have this kind of approach. Empty, last is returned. Otherwise, you declare a pointer, right? Remember, I talked a little bit last lecture about smallest. Initialize it to not 0, I said, but to the first element in the range. And then, if move to the next element is not equal to last, so you can see here a combination, and you can use this style. Plus plus first means move the iterator to the next location. Compare that location to last. So this is the operator which is specific to forward. It's not provided by output and input. That's why forward iterators are important. So you have to think why we don't have input or output, because all we do is we go through the next element and compare. So while this is true, we compare, dereference the location, okay, and dereference this location, given for smallest. And if this is smaller, you have to update smallest. And you are working here with pointers, iterators. Smallest has now the location of first, so it's iterator, it's not elements, be aware, and returns smallest. So minimum element returns a pointer, an iterator. In order to work with that, if you look for a minimum element in a range, you have to dereference it. Now, for your assignment 2 part 2, you will have to work with this because you will see your vector comes with a pointer to P, which is called iterator. And you have to push back elements where you might use or not use iterators, but erase an element to which you have a pointer or iterator. You have to think about using something similar. So I recommend you to look at this example if you have trouble with that erase element to which iterator points. And then, as you can see here, in order to use it, the smallest element, after things are constructed, you have to dereference it to find the element. Dereference, and they use the strictest notation possible. And this is how you work with ranges coming from arrays, C arrays, another thing which you might need for your assignment 2 part 2. You will see you have at some stage to work with ranges. You know the size, therefore all you have to do is use this notation to make sure that you are going to the end, which is in fact the one past the end. Right, so these are, as I mentioned before, very good places to look for examples of other function templates. Disadvantages, not always easy to understand. What is the return value? A value, an iterator, or something else? Because algorithms are performing specific tasks, for those tasks they need a specific type of iterator. For minimum in range, as you can have seen, you need forward iterator, but for sorting you need random iterators. Therefore, minimum element can be applied to any container because most of them provide forward iterators. But sorting cannot be applied to any iterators, only to those providing random access, which are C arrays, vector, and double-ended cube. And if you apply the algorithm without knowing this, you get garbage, as we will see in an example I will show you. So, you have to know exactly what are the requirements for the algorithm in terms of iterators, and then what type of iterators are provided by each container in order to make them work very well. And combination, sometimes you have combinations of algorithm and containers, but they don't give you the best performance. And this is another issue which comes from, learn about it from references. Minimum and maximum element. And as you can see here, we have constructing a vector with pushback, and we take some values, and then we look for the minimum element we have seen, dereference it, and we work with a whole container. Right. And the same for maximum. So algorithms return iterators in the container, not values. Find, then if you think about find and what kind of operators should the iterator for find provide is you look at the first element compared to this one. If it's equal, you have found it. If not, you move to the next one, to the next one, and to the next one. So find needs only input iterators because you have to move forward. But sometimes the best thing would be probably forward to use because it doesn't come with a lot of overhead. And here you have to know that find returns an iterator to the element which in the case the element is in the container, but otherwise returns the end of the range. So you shouldn't dereference automatically find. Okay. You shouldn't, because if the element is not there, you will try to dereference the end, and the system will say, oh no, you are doing something stupid. So the proper way to do it is, if this is not the end, it means that the element was found. So this is classical way to work with algorithm which return past the end iterator when it fails to perform its task. This is the way to work. So in this case, 14 was found, and what you want to do maybe returns a location. And here you can access the value or the position or move to the next element after 45 or remove it if you want. Be aware find returns the first location. If there are more than 145, only the first one is returned. So, types: non-modifying, modifying, removing algorithm, mutating. Mutating means, so removing elements, mutating, or reorganizing data in container, like permutation is reorganizing. Sorting algorithm, sorted range algorithm, so you can apply the algorithm on the whole container or on a sequence, a range called, and the numerical. So non-modifying require input or forward iterators. So, and the typical example, minimum and maximum, but this is some list of how many algorithms you can use to perform counting, how many elements are there, counting with a Boolean expression. You have an expression counting how many elements are greater than 5, count if, and you have to provide 3 arguments. The range in which you look, and the third argument will be the criteria. Min and max, you see, find, we have talked about. Again, find if. As you can see, many algorithms come in pair, count and count if, find if. And you will see this approach for other algorithms. Searching, first n consecutive elements, searching in a sub-range. If you want to look at what is the last element matching your value, find n, search for the last occurrence. For the first of several possible values, find first of, and you provide here the range to look in, and a set of elements. And the algorithm looks for the first element in the set, which is in counter, it returns its location. 2 ranges are equal when two sequences differ, lexicographical compare, so you can compare based on ASCII table. As you can see, a lot of them are there, but how to use them, and it's a different story. And the way is go to the reference bar. Now, for your exam, I assume that you will be familiar only with those for which I provide some code. Like here, for each, I worked with min, max, min element, max element will be similar, so you don't have to worry about knowing all this algorithm, but general information for them would be a good thing. Now, for each is a step up of for loop, and the basic for loop is for starting value, go to a less than ending value, and increment the counter. This is a basic one. Next up is for ranges, for element going through a sequence, perform a task. Now, this for each is the on top of for ranges, because you can provide a third argument, which is normally a function returning one value or returning no value, taking one argument. This is a condition. Take a single argument, and this function is applied to each element in the range. So Haskell has similar function. Assumes that we have this print, it takes one argument, and all it does, it displays the element and followed by an empty space. When we declare our constant vector, there is this for which does not modify this. So be aware, it returns another vector, is non-modifying. So there is a version of for which is promising to not change the range on which it works. We will see there is another one where it changes the range. So with this one, all it does, being a non-modifying, applies this print function and display whatever elements were stored in V. And being a non-modifying, it can work on any constant variable. So be aware of constant least, constant double-ended Q, and stuff like that. Now, some algorithms which are not non-modifier won't work. That's why you have to know the bits and pieces. The second group is when we modify elements. So there are two ways to modify. One is modify the elements in the container, or change the elements but store them outside in another container and return that container. So the elements are copied into a destination range, but the original source range is not changed. In this case, both the original range and the destination has to be specified to the algorithm. And again, for each copy backward, we will look at copy because it's a very cute algorithm and useful algorithm. You can copy from end to last and store in a range transform, merge. Now, merge two ranges. Remember, if you have done 201, in order to merge two ranges, normally they are sorted. And then merging, you get a sorted range. If you merge two unsorted ranges, you get garbage. So for this one, you have to be aware, merges two ranges which are sorted in order to obtain a sorted range. Swapping elements, replace each element with a given value. So you have a range and a given value, you replace each element in the range given by the third argument. You can replace only a specific number of elements. You can have some algorithm here. Replace if, again, with some condition, criteria is used. Copy if. These are some common tasks you might have in your problems to solve. Now, for each is in this case used as a modifying algorithm. We have a function, again, which takes one argument only, but it has to be by reference because it's meant to change that element. Okay? So what we do, we compute the square of its argument. And now we have something like before, a vector constructed, and with this for each, we have the elements from this to this applied the function we have seen, and then if we display after this the vector v, we get 0 square, 0, 1, 4, and so on and so forth. So as you can see here, we have a for loop where some function is applied inside, but instead of 2 lines of code, we have this algorithm which does a very efficient job. How to remove elements? You can remove elements with a given value or based on a given criteria, or copy as a result the elements not verifying a given criteria, elements which do not match something, adjacent duplicates are removed. So you get here the initial range unchanged, but the last part is obtained from the initial range with no duplicates. And then shuffling elements in the container without changing their value. Reverse, it's very nice how to check for a palindrome. You just check the initial value with a reverse value. And it's one sentence to perform these tasks, which is normally a little bit more involved if you have to write the code yourself. Reversing their order and copy the element in another range. Rotate is used in graphics a lot. It's moving the elements like a permutation. You can randomize the order of the elements, so you shuffle them in the container. Partition is what you know from mathematics, 1, 2, 3, and then you can partition 1, 2, 3 as a second thing. Now, one common task is sorting. And sorting doesn't change the value of elements in the container, but the order. So it's a mutating algorithm. This algorithm have worse than linear complexity. Normally it's n log n something with best performance. And because it has to shuffle the element, it needs random access. Therefore, only the three containers, seed arrays, vectors, and double decks are working with sort. It's very easy to use. If you have a container providing random access, then all you have to do is specify what is the range you want to sort. You want to sort the whole container. That's very simple. It's based on less comparison for integers and other numerical values. C has a sorting algorithm, but it's a nightmare to use, probably you know. It passes a third argument to a comparison function, which is horrible in terms of syntax. While this works with C array, with everything else. For lists, you don't have the possibility to apply this. If V is a list, you have to invoke V dot sort. The list comes with its own sorting function. So, with this, the content of V is changed. After that, if you display the elements in V, you get them in sorted order. Sorted range algorithms, it means that all these algorithms, in order to work, have to invoke only sorted containers. They work fine for set maps because they are already sorted, but they work on vectors. The typical way to use any of them is first you sort the algorithm and then you call binary search, or you call merge with two sorted ranges. You know, this binary search is one of the fastest searching algorithm you can have. Two merges the elements of two ranges, right? It is a classical approach for sorting data. Merge sort is called. And here, as you can see, we have set operations which are not included in the set container. They are algorithm, global algorithm to compute union, intersection, and differences, symmetric differences of sets. They are what you know from mathematics. So, here we have a garbage in, garbage out example. Because we have a vector where we put some random values in it. And what we have here, we go with I, with a 4 ranges, right? And notice bool alpha forces the compiler to display true or false instead of 0 and 1. Bool alpha is in IO manipulate, it's a manipulator to format output, and displays, instead of numerical value, these lovely Boolean values. And what we are doing here is invoke binary search on this vector, and for each I, we look for that I should display true, true, true. Because it's something like this, V begin, V end, so we start at 0 location, And whatever element was stored there, it's a random value, it's the first element in the vector. And we ask the binary search to find that first element. Okay? And then with the next approach, we ask the binary search to tell us whether the second element is there, and whether the third element in the range is there. And as you can see, first two are true, which is the correct one, but for the third one, we got false. And this is expected because this binary search algorithm works properly if data is sorted, which is not the case here. And if you know how binary search works, you can understand why this happens. So in order for this algorithm to work, after we have designed this, we have to invoke sort v begin v end, and then apply this. And then you will get true all the way. So these are the bits and pieces you have to know about algorithm in order to make the most use of them. Algorithm numerical are very useful algorithms which perform various common tasks like accumulate for us. Look at this example. You have to include this file for numeric algorithm, be aware. We declare a vector and we want to compute the sum of all elements in a vector without using for loop or while loop or any other thing. Accumulate does this. It's such a common task to compute the sum of sequence of elements that it was transformed in an algorithm. And all you have to do is specify what elements you want to add. You can start and use some range, and what is the initial value for your sum. If you want to compute the numbers and add to 10 the sum, you provide this third algorithm as 10. I think my this stuff. Probably I have to stop. And I will stop. So as you can see, this does combines all element values with sum. We don't have anything with product. And you can specify an initial value from which to add. If you put 10 here, it will say 10 plus 1 plus 2 plus 3 plus 4. If you put 5, 5 plus 1 plus 2 plus whatever then, 10. And as we add integers, it returns an integer. So we still have some time. Provides a large group of algorithms, and they are split into different groups. For your assignment 2 part 2, you are not allowed to use any of these algorithms. I want you to practice to see what is behind this algorithm. So assignment 2 part 2, you are not allowed to use STL at all. You have to start from scratch, writing the algorithm. And whatever I have covered here and whatever is presented in the tutorial, you will be familiar with. So I like this copy algorithm because from now on, when you design your types, you can use copy to perform a lot of tasks for copy constructor or for assignment operator. Not with your assignment 2 part 2, but from other tasks you may want to use this. And because copy, as I said, requires only output iterators. Notice how in this example we have a list object and we have 5 elements where we initialize a list, and then to display the elements to the output stream, we just use copy this range where to the output stream. And then we have a vector, and you can construct a vector from a list. It's very easy to change the list to a vector. All you have to do is, for the copy algorithm, provide the input range and where to put the result. Start at this position and end the elements. And again, you can display data. So as you can see, this copy does a lot of tasks which can be quite challenging if you are working to convert from list to vector, or you have to do the size and then begin end of the list and copy it here. And as you can see, we have ended up with the same output. We don't have to worry of how many elements are in the list or how many elements are in the vector. Begin and end, remember they return iterators and you work with them. If you are careful to follow what is required. So this finished our discussion about standard template library. You have seen there are a lot of tools there. Time is required, but there are benefits. They are correct. They are tested by many people besides the creator of them, and they are coming with efficiency claims. So if you look at the reference page, you see this algorithm is linear, which is the best efficiency. Constant time is the best efficiency, but linear is next best. Quadratic time is a little bit more. Normally, if you write a sorting algorithm, it's in quadratic time complexity. But in the library, the sort algorithm is better. It's n log n, which is much better performance. They do a lot of optimization to get that efficiency. So, assignment 2 part 2 is out. Please read it and prepare your questions about it. We can talk. Do not leave it to the last moment. The due time is not this Sunday. Next Sunday, you know everything you need in order to solve that assignment. I left out the exception. You don't have to worry about them. Just concentrate on using templates and dynamic memory allocation. So in order to solve that example, you have to look a little bit at how the move constructor was defined, how the move assignment was defined when we talked about them, and adapt it for templates. It's not, it's analogy. Right, thank you very much. See you tomorrow.